Hi everyone, welcome to my presentation for the IROS 2020 workshop, Learning Impedance Modulation for Physical Interactions, Insight from Humans in Advance in Robotics. So my name is Ludovic Righetti, and today I would like to talk to you about impedance modulation and ask the question, is it a necessary trade-off between environmental uncertainty and external disturbances? And I'd like to try to make the case that indeed the way we want to modulate impedance is rooted in the trade-off between trying to reject external disturbance and deal with the fact that we don't know the environment very well. So what do I mean by that? So why do we actually care about the impedance modulation? Why does it actually matter? So let's take an example. So if I show you this, this picture, and you see that there's a hand holding an egg, and we're going to ask the question, say, is it, do I need basically to do this task? Do I need to have a high impedance, low impedance? So here we can think about, for example, the stiffness of the fingers. Does it actually matter? So we can actually say that if I knew exactly what was the shape of the egg and I had perfect control of the fingers, I actually can do the task with zero impedance in principle, saying that if I have just a feed-forward plan that I could compute and I execute it, I'm going to have exactly the behavior that I expect, and I would be able to pick up the egg, right? In reality, since things are not exactly how we model them, it's probably not going to happen, and I will need to do some level of feedback. It means I need to be able to adapt what my fingers are doing to basically what the environment and what the actual reality is. On the other side, if I have a high impedance in the sense that I'm going to basically make my fingers stiff and try to keep them in a certain position, if I try to pick up the egg, it might be a problem because if the egg is slightly bigger that I thought, or if my fingers don't go exactly where I thought they should go, what might happen is that I might break the egg, right? So it might be really bad because if I have very high stiffness, I'm going to apply a lot of pressure. So the resulting force that I will see on the egg, it's going to be very high, and that might be a problem. So here we might think that, okay, we need to be able to react to the impact that we have, such that we don't just rely on what our belief of the feed-forward command should be, but at the same time, the reaction should be soft because we want to have a safe interaction. All right. Here's another case. Here we are jumping, right? So we have a kangaroo that is actually jumping. When it's going to go hit the ground, what kind of behavior do we want? So here, if you don't know exactly how the ground looks like, what will happen, what might be good is that we want the legs to be rather compliant, right? Such that when it hits the ground, the legs will bend and behave like a spring, and it would be very good, right? And what is especially nice that if you do that and you don't know exactly where the ground is, you're guaranteed that you're not going to create a pretty big reaction force that might destabilize the kangaroo, right? So from looking at that, we could say that basically what we want to define, right, for the impedance is basically the reaction to uncertainty and basically the reaction to physical contact that we don't necessarily know where and when they will happen. So in that sense, it is really about feedback, right? How do we design reaction means how do we design feedback in a sense. And from what I just explained, we could imagine that compliant means low impedance is a good idea because it will improve physical interaction. Is it really true always? I think it's a question we can ask, and the answer obviously is not really always. So let's take another example of grasping and locomotion at the same time and see if here it makes sense to have compliance. So this is an example of a rugby player, Chabal, who is a famous French rugby player, who is actually holding a rugby right here. So here you could argue that basically in order to deal with the external disturbance, which is basically the player from the other team, you want to hold the rugby really, really tight, which means that the rugby ball, which means that basically you need to be very, very stiff in your holding in the fingers, in the arm, such that you can reject the disturbance that is actually coming. In the similar way, you could argue that here you might want to be very stiff as well, right? So you want to make sure that when you're going to have an impact, this is not going to move, right? So you want to make sure you don't lose the ball, you don't move. The rest of the body might be rather compliant because you want to be able to absorb the shock, But still, here, high stiffness is extremely important to be able to achieve this task. So high stiffness might be a very good idea when you have external disturbances. Here's another example. This is an example of Lorena Ambreux, who is a parkour athlete. And so she's doing a backflip in an environment, which is the top of a building. And here she's going to reception herself, right? When she hits the ground here. And here you could argue that here, do we want to have low stiffness? Sure, that would be great, like for the kangaroo. Do we want that she behaves like a spring? Probably not, because otherwise she will bounce back, right? So what you would like to have here is that when you hit the ground, basically you want to absorb the high velocity impact that you will have. In order to absorb the high velocity impact, what might be a really good idea is to have a lot of damping, right? Very high damping might allow you to dissipate velocity very quickly, because the impact is really basically suddenly you're going to have a shift in velocity because of the hard impact on the ground, and you want to be able to dissipate that really, really quickly. So from these two examples, we can see that basically high stiffness and maybe also high damping in certain situations will be very, very helpful to deal with impacts and to deal with external disturbances. So this goes against this idea that we need to be compliant all the time. Actually, we maybe don't. It's good to be compliant sometimes. It's good to be stiff sometimes. It's good to maybe have low stiffness, but high damping sometimes. And sometimes it might be good to have the opposite, right? So the big question now is, how do we deal with that? One of the hypotheses that I'm making in this talk is that the modulation of impedance, it's something we need to think about it in a way to trade off between trying to reject disturbances, absorb impact, and also handle the uncertainty that we have in the environment. And how do we deal with that? That's basically what I'm going to try to discuss today. And one of the questions, how do we compute that automatically? How do we automatically find good schedules for the impedance, so impedance variation over time, depending on where we are in several tasks, right? So here's an example of a task where if you have a quadruped robot that we have in the lab that is jumping, the problem here is great, but when it hits the ground, right, you see it's actually bouncing. It's really not the kind of behavior that we want. What would be nice to find an automatic way of getting a robot to actually jump, and when it hits the ground, you have perfect reception in the sense that there is no bouncing, right? And here what you want is basically you want to have high stiffness, low damping when you take off, because you really want to follow and to kick as hard as you can and follow the desired trajectories that allows you to get very high. And at the same time, when you're going to hit the ground, you want to have low stiffness, but you want to have very high damping if possible, right? And how do we reason and build a model such that we can compute those things automatically? So today I'd like to talk about two things. I'd like to discuss one approach that we have proposed, that we recently also submitted, like a few days ago, to ICRA, which is a risk-sensitive optimal control. So basically how we're going to explicitly model the uncertainty about the contact when we're walking, and how we can do that such that we get the behaviors, the desired behavior that I was discussing just before. The second thing that we would like to talk, that this is a work that we're actually presenting at IROS this year, so you can also check it out. And it's basically how can we include explicitly impedance control when you learn neural network policy, when you do reinforcement learning, such that we can not only learn a policy, we will learn a policy that has meaning, that explicitly encode a variation in impedance and also desired position. So let's start with the risk-sensitive optimal control. Question is that I would like to do optimal feedback, right? That might be a very good framework to compute impedance modulation. As I said, the impedance modulation is really about the reaction, so it's about feedback. So can I just use standard feedback control design to compute those impedance behaviors, right? And that's a legitimate question. So I have very good tools. I can do H infinity, I can do LQR, I can do a lot of different things to compute feedback gains. Can I just use that, not think too much about it, and everything will be fine, right? So if I have a robot, I have a dynamic model for my robot. So here it's a discretized dynamic model for my robot. I have the state of my robot. I have the control. If I do, for example, I do iterative LQR, what I can compute is a feedback law that's going to control. It's going to be some gains, which basically defines the stiffness of the joint of the robot times the state of the robot plus some feed-forward term that describe the task that we're trying to achieve, right? That's pretty standard. So we could do that, and we actually tried to do that. So we put this on the humanoid robot. We did basically LQR on the full dynamics of a robot. We did it in such a way that it's consistent with the contacts that we have on the ground. So this work by Sean Mason. That was in my lab. And it works really well and everything is great. Here's the catch, is that so what is great is that if you do that, basically you can take into account all the coupling with all the degrees of freedom. You can really have a nice way of, so you control the forces that you get on the ground. It's great because you can really define a performance cost. You can really define what you care about, and you can automatically compute what is the control that you get in order to minimize a notion of optimize the notion of performance. The problem is that if you do that with LQR design, you will tend to have very aggressive gains. It means that you will have very high stiffness and damping. And this makes things problematic because sometimes they don't work on the robot. If you have too high stiffness and damping, it gets your robot unstable. The other thing is very, very hard to deal with contact transitions. So especially when it's uncertain contact transitions, when things happen before or after we expect them to happen, usually things go wrong with this kind of designs. So it's very hard to follow a schedule of gains when things don't work as planned. There's another issue is that basically the gain schedule that we have tends to create everything very stiff, very high impedance, and we don't know how to, you cannot create compliant behavior when it's actually needed, because the only way basically to reduce the gains is to increase the cost in the control. And so basically you increase the cost of the control, you reduce the gains, but that's not what you want, right? What you would like to reduce the gains basically when there's a risk that you're going to hit the ground in a way that you don't want. So what is the issue? And what is the big issue when we do that? And the way we did it basically is that we basically do not take into account the fact that the environment is uncertain. And at least we don't do it in a way that makes so much sense. So basically we don't model, we don't model the environment in the sense that the dynamics of the environment is not something we want to model because we don't know it. We are working in environments that are uncertain. But we don't really reason about this uncertainty. And what does it mean, and what might be the consequences of this uncertainty on the dynamics of the robot. So what we would like to do, and what I would like to show you now, is how do we explicitly include this uncertainty? Maybe the contacts are not where I want. There might be uncertainty in my measurements. There is going to be uncertainty in my model as well, in the sense that my model is not perfect. And I want to model the fact that there's things I don't know about my model that would be basically unmodeled external forces, right? And basically, how do I design a controller that is going to be explicitly sensitive to this uncertainty? So let's go back to the basics, right? I have my process model that defines the dynamics of my robot, that is a function of my state and my control. And I'd like to add some noise here. So what does it mean when I add noise here? So when I add actually some uncertainty here, which here I model as a noise, that's process noise. Basically, it describes an external disturbance. So when I add noise here, it means that I describe uncertainty in the sense that it's an external physical force that I do not know, so I consider it stochastic, that will change the actual state of my system, right? This is actually something pushing me. Another way to include uncertainty is to look at the measurement model. So the measurement model, right, is basically what you have when you design a Kalman filter. You always have a process model and measurement model. Measurement model basically tells you how the sensors that you have, so what you measure in your system, is actually a function of your states and your control, right? And usually you add noise here. So what is this noise meaning? So this uncertainty that I have here, this is basically, for example, Gaussian noise, right? This uncertainty is basically going to be the lack of information that I have about the world. So it's not about a physical process. It's not that I'm getting pushed. It's that there's something I don't know, right? So for example, the uncertainties that I don't know where the contacts are, it's basically something that comes from the measurement, the lack of information. It's not about unmodeled physical forces. And but I'm insisting on that because I want to show that basically take this into account. It's going to help us compute impedance profile that makes sense. So basically the question is, how do we put this into optimal feedback, and how do we basically trade off the fact that there's external forces that we don't model, that we want to be able to be robust to the external disturbances, and how we trade off also the lack of information, so measurement noise, into an optimal feedback controller. So the typical thing, right, if you do, so I'm going to show you how we add this. So the typical thing when you do optimal control is that you define an objective function, right? which is basically as a terminal cost. It's a sum of running costs over a certain horizon that you want to optimize for. You have a certain dynamic model that tells you what happens. And since here we have a stochastic model, usually what we will do is that we're going to minimize the expectation of the cost, right? So we want to find controls, control law u that may be a function of x, right? If you have to feedback, that will minimize the expectation of the cost that I chose for you, right? So that would be the optimal thing to do. So if you do that, right, for linear system, you can do iterative LQR or iterative LQG in this case, because you have uncertainty that will efficiently find local solutions. And the local solutions, every step will be basically a control that is a feedback law of the current state plus some feed-forward term, right? So the feed-forward tries to achieve the task, and basically this tells you how to reject disturbances. So this is great, except the problem is that when you just do LQR or variations of that, is that distributed solutions completely ignore what this noise is all about, right? So the LQR solution basically tells you that the gain is independent of the noise. As soon as the noise has a bounded variance, the solution, so for example, Gaussian noise, right? The solution to the LQR, so this matrix K's that you compute, basically they are independent of what the noise is actually doing, which is a little, that's not exactly what we want, right? Because you say if the variance of the noise becomes high, I would like K to go up, and if the variance of the noise go down, I would like K to go down, right? In principle, that's something that sounds reasonable. So what people did, actually Jacobson in '73, is a risk-sensitive control. So instead of taking the expectation of the objective function, I'm going to take an exponential transformation. So I'd minimize the expectation of the exponential of some sigma, which is a positive variable, times L. And so if you do that, it's called risk-sensitive control. So you can solve this problem. In the linear case, basically you get Riccati-style equations, so you can solve them the way you solve LQR. But the really interesting thing here is that if you look at the expansion of the log of J, what you see is that basically what you actually minimize is the expectation of your cost, right? So that's the average cost. That's exactly what we were doing before. But in addition, it's going to be a weighted sum of the higher order moments of the distribution. And the important one here is that basically, since if you take sigma to be positive, it's going to tell you that if you have a high variance in what you do, which means that basically the variance of your cost means that because of the uncertainty, your cost might change a lot when you actually execute on the robot. High variance should be penalized, right? So basically what this will tend to do what is called a risk-averse control, which means that you try to avoid taking risk, so try to find solutions that will minimize also, not only minimize the cost, but also minimize the variance of the cost, which is a good idea, because that's basically taking into account the risk that you're taking when you do something. So this is great. And basically Farbot Farshidan a few years ago found an LQR-like algorithm to actually solve this problem, which is great because then we can use the typical algorithms that we know. And then we can find a solution of this type, where basically now in this case, the control K, the control matrix K, will actually, and the feed-forward term will explicitly depend on the actual covariance. So assuming you have Gaussian noise, it's going to explicitly depend on the covariance of the noise. So now as the covariance of the noise, for example, increase, K will tend to increase. And as the covariance of the noise decrease, then K is going to decrease, right? So this is almost what we want, except that I've talked about process noise, but I've still not included the fact that I have lack of information, right? So I have not discussed about the measurement model yet. So I don't know how to include that. So what we did a few years ago, and this is really the work of Brian Planton, who was a PhD student in my lab, was to say, how do we include that? And I'm not going to go too much into the details, but the idea is that, so if people have looked at this in the past, and the problem is that if you want to do that, depending how you want to do that, you end up having solutions where you need to keep an infinite number of these measurements, and the problem becomes very quickly intractable. So the key idea that he had said, instead of looking at that directly, we're going to build an extended Kalman filter along the trajectories when you do iterative LQR. We have let's say a desired trajectory that we want to that basically is a solution of the initial guess for the optimization. And what we're going to do is that we're going to build an extended Kalman filter along this trajectory. And so once you have a Kalman filter, basically you have a system dynamics, which is going to be the estimation dynamics, right? Which is going to look like the process dynamics, but that is going to have the Kalman gains in it that basically depend on the covariance matrices of these two noises. So basically now what you do is that you stack the process model, the estimated dynamics on top of each other. So you double basically the number of variables that you have. And now if you do that, so if you want to look at the details, look at the paper, but basically the key idea is that if you solve that, we can come up with an LQR-like algorithm that is very efficient as well. So now we can also find a controller that looks the same as before. So I have a matrix K that defines the impedance. So basically the force production as a function of the state measurement that I have, plus a feed-forward term that defines the task that I want to solve. And in this case, what is really nice with this algorithm is that now our K is not only going to depend on the variance, the covariance of the process noise, but it's also going to depend on the covariance of the measurement model. So in a nutshell, what happens is that K is going to go high if the process noise, the variance increase means I get much more disturbances, so I need to be more stiff. Intuitively, and what's going to happen is that if I have a lot of uncertainty, which is what we want to use in contact, then the stiffness is going to go down, because as we get more uncertain, we don't want to take too much risk, right? So now we start to have the kind of behavior that we want. And we tested that on the TOEIC model in simulation, and it was kind of working the way we expected. So now the idea is that can we use that for actually more complicated tasks, which is basically locomotion task. So this is the work of Bilal Hamoud that just submitted this work to ICRA. And what we did here, the question is, say, can we model basically what we want? And I won't go into the details either. Bilal will describe this more in the workshop. He's participating, and you can also look at the paper on Archive. So basically, the idea here is that we're going to model the uncertainty as a Gaussian distribution, the uncertainty in where the leg is. And when we optimize what the robot needs to do, we're going to explicitly model the fact that we don't know exactly where the foot is, which is going to implicitly include that we don't know exactly when we will hit the ground, right? And by modeling this uncertainty explicitly and using the algorithm I briefly described before, we're going to be able to compute stiffness and damping gains that go that along the trajectory that will vary over time to try to achieve the task. So here's an example where we do a very simple thing. We get the robot that is on 3 legs. We move one leg. So there's different ways of including this noise. So here the idea is that we just model this as an ellipse, so it's a Gaussian distribution around the foot, and then you can project this back in a contact consistent manner into the full dynamics of the robot. So the details are in the paper, but basically here the idea is that once you have that and you hit the ground, if the ground is not exactly what you expect, but let's say, for example, the ground is higher than what we planned, what happens? So we studied that, and what is interesting is that you can compare what you would get if you do DDP or iterative LQR, which is the same, right? And what happens when you do what we propose to do. And what is interesting here is that these are the gain matrices. So that's joint stiffness matrices, right? So basically this maps the delta X in all the joints of the robot, right? So front left, front right, hind leg, and hind right and hind left legs. And that's basically the joint torques that you get, right? So this is basically a view of the matrix, of the gain matrices that we have. And what you see is that for the iterative LQR, we get, so first what we get is that in magnitude, we get much higher magnitudes than in our approach. So here we get almost an order of magnitude reduction in the gains, which suddenly makes them in the range that is actually runnable on the robot. But here the gains that we have here, we don't think that this would work on the robot because beyond the kind of maximum gains that we can use. The second thing is actually the pattern completely changes. Here you see that there's a lot of stiffness included in this is the swing leg, right? So the left leg is actually the swing leg in this case, so there's a lot of stiffness involved here. Where here the stiffness goes away and all the stiffness is redistributed for the leg here, which is basically this leg here, which is the right leg, and the back on the left leg, right? So basically the leg that are going to compensate for the fact that we don't know what the swinging leg is doing. So here we have really a meaningful redistribution of gains by doing that. So we can execute that and see what happens. So what happens, we try different types of models. So I don't want to go too much into details. There's different ways of including measurement noise. So in the models that we included is the risk, it's called risk context. It's the green one. This is the reference one that is optimized with the optimizer, which is it's the same as for DDP. And this is the reaction you get with DDP, which is LQR, right? It's the same thing. So here, this is the gray zone. This is where the contact happens, and here that's the end. That's where the contact should have happened, right? So you see that there's 150 milliseconds between the moment there is actual contact and the moment we have planned to have contact. What happens if you look at the blue and if you look at the green? So the green, that's our approach, says that suddenly the reaction force that we get for the left leg, the swing leg, is very low. It's twice as low as what you would get with the normal DDP. So what happens is that overall, at the end of the trajectory, the DDP diverges because it creates a lot of forces, it destabilizes the robot, and eventually it falls. But in our case, the force is lower, and then that's when the desired force happens. You manage to actually apply close to the desired force, and everything works out. What is maybe more surprising and interesting is that what happens on the front foot leg, right? Which is basically this leg. What happens? What are the reaction force that we get? Here we're looking at the vertical reaction force, right? You see that for the blue one, so that's the DDP, basically, so the moment that you have the impact here, what happens is that you have a lot of variation in the force, in the contact force, right? So because we have a contact that was not planned, there's a lot of disturbances that actually happen, that appear on the other leg. And eventually this leads to the fall, right? And for the green one, what happens is that there's a contact that happens that was not expected, and this doesn't have any effect on the actual force that the right leg is producing. So it means that we can absorb completely the unexpected impact directly with the swing foot without having any consequences on the other leg, which is very interesting, right? So we continued that, and we tried this now on the quadruped. So we tried that on the quadruped for a jump. So this is the video that you can see here. And you see that so we optimize the motion so that the robot can jump, and we compared basically our approach with DDP. And what you see here is that suddenly we had basically a new ground that is higher than was expected. Then the robot jumps, and what you see here is that basically the DDP is going to bounce while our approach is not going to bounce at all, right? It's going to stay on the ground. So this works actually better than expected, which is what we wanted. And here very quickly, what you see is that for the reaction force is reaction force of the legs when it takes off. So when it takes off, we get a similar reaction for DDP and this our approach, which basically you get a very high stiffness and try to jump as much as you can. When it hits the ground, basically what we see is that the reaction force that we actually get in our case is lower, is roughly 20% lower than we get with DDP. And the other thing is that we don't get a bounce. So here you can see that there's the bounce in the case of DDP. In our case, there's no bounce at all. And here's maybe the most interesting part. If you look at the norm of the joint matrix, the stiffness matrices that we get, in our case, the norm is much lower, right? The green one is much lower than the norm of the matrix, the stiffness matrix that you get with DDP. Again, it makes it more reasonable to run on the robot. The second thing is that we see the similar pattern in the stiffness modulation. That if you look at basically the norm of the damping matrix, here we see a completely different behavior. It means that during the flight phase, our approach increases the damping. It means that, so the DDP decreased damping during the flight phase. In our case, it anticipates the contact and increases the damping a lot. Basically, it foresees the fact that it's going to have to dissipate the impact. So this is very cool, right? Because it basically tells you that you need to dissipate the impact. So increase damping and make sure we'll be able to dissipate the impact quickly, while being very compliant in terms of stiffness, right? So this actually leads you to the behavior when you jump and you hit the ground, and you don't rebound, and you have a very nice dissipation of the impact. So now we did tests for the quadruped trot also in simulation systematically. So here we vary the ground randomly, and we did 1,000 different types of simulation, and you see some of the simulation here. So our approach statistically works better in other ways, but it tends to work better than using the basically same trajectories, but with the LQR design. We varied the ground up to 14% of the leg or 11% of the leg length. In our case, it's always better than the DDP case, and we can increase quite a lot, actually. You can see the performance. Another interesting thing is that if you look at basically the base positions, the base of the robot when it's walking in the air compared to desired, our approach tend to trade off tracking. So basically we get much less good tracking, but we get robustness out of that, right? So there's always this trade-off between tracking and robustness. And here we can really have this nice trade-off, say we don't track as well, but we're much more robust to uncertainty. All right, so that was for my risk-sensitive optimal control discussion. And I hope I convinced you that basically this approach to complete optimal impedance makes sense, and it makes a lot of sense to explicitly think in terms of disturbances and lack of knowledge and uncertainty. So now very quickly, I'd like to go through the problem of learning impedance policies. And I won't spend as much time as I just did on this one. So the question we ask is that, does it actually matter to model impedance control when you do reinforcement learning, right? So in principle, whatever mapping should work, right? So if a lot of people do, you map the state, you have a neural network, you compute the torque, and any basically function approximator that maps states to torque should be good, right? So there's no need to have any structure in your policy, and that's true. In principle, you can approximate any function. You can also do the same to the position control. So basically what you map is the state of your system to the desired position that you would like to see for your joints, and you can approximate, any neural network should be able to approximate the policy in a way that is nice, right? So this work that we're presenting at IROS, so you can actually check it out now. So I'll spend a little bit less time. But the thing that we said is that actually, what if we don't know the environment, right? So if you have a change in the contact location, in the friction, in the rigidity of the surface, does it change anything, right? So assume you have a controller where you have a desired force, you have a reference trajectory, and this is the feedback, this is the damping, the stiffness, and the damping matrices, right? What we claim and what we need to study is that if we separate the feed forward, right, which is the desired thing you would like to do, from the feedback path, which is basically the gain matrices that you have, does it help into learning, and does it help in creating more robust policies? And the hypothesis is that this is beneficial actually to separate these two paths, the feed forward and the feedback. So basically, how do we plan our behavior and how do we correct for errors? And it makes things easier. So what we did is that we learned a neural network that is specifically encode a desired position and desired stiffness and damping gains that can vary over time depending on the state, right? And then we combine these two things to generate a control law, the usual way. And we tested that in two tasks. One is the manipulated and is to apply a force on the ground. And we, on the table, and which varied the table height, the friction that we get on the table, and also the stiffness of the surface. And here I won't go into details, but basically red is pure torque control, blue is pure position control, and the green is the variable gain approach. And you can see that in the green, it systematically gives you higher performance, and also the variance that you get for, if you do that 100 times, you try to train your neural network, you get a variance that is much lower. It means that it's much more repeatable that you will get out of those. We did the same for a robot that tries to hop. So it's just a hopper that tries to jump up high, and so we constrain the base, so it just jump up and down. And here you can see that, so position control is very hard to get right. But for the variable gains, again, we tend to learn a little faster, but mostly we learn with much lower variance in terms of the results that we get, which is great. So basically we can get things to be very robust to basically variation, for example, in stiffness and things like this. So learning impedance policies improves the robustness to a known environment. It helps to learn more robust policies, and it seems to be much, actually it's just because it seems that it's easier to learn in this way, because you can explicitly separate what is the task and what is the way to react to uncertainties. And also improves the learning speed, but mostly it improves the repeatability of the learning. So we basically took the best PD controller with fixed gains, very low gains that we could find. Then we took the one that we optimized with variable gains, and we tried to directly put it on the robot. And this is what happens. So in that case, we are able to actually get better performance with our approach to a fixed gain. So that was the best we could get with a fixed gain, right? With low gains, it was the only one that works with using low gains. And then we started to move, we can randomly move the contact. And you can see that it actually does something reasonable. Right, so we can actually move the environment, and it keeps working well. So it actually validates what we're doing, but it seems that it's actually easier to train this way, and it makes more sense. All right, so here I quickly try to convince you that it makes a lot of sense to explicitly include impedance goals when you do reinforcement learning, and just not learn blind policies, but learn policies that are meaning, and that separate what is feedback and what is feed forward. It actually does, at least in the experiments we tried, it does improve repeatability, and it actually improves the robustness to uncertainty in the context. So again, dealing with uncertainty in context is the thing that we really care about here. So that was a little quick, but I hope I convinced you that it makes a lot of sense to try to modulate impedance in a principled way to deal with uncertainty, and that the lack of knowledge is actually one of the things we want to explicitly encode, either explicitly when we do optimal control, or implicitly by putting structure in what we learn using reinforcement learning. A lot of people involved. So Brian's the person who came up with the idea of including measurement uncertainty in restrictive control. Sean is the person who tried the first time the whole body LQR with contact consistent design for the humanoid I showed you. And Bilal is the person who actually did all the experiments of the quadruped and designed the measurement model for the quadruped and show you all the cool results I showed you. And Majid did a lot of the experiments I showed you with the quadruped, and Miroslav is the person who worked on the variable stiffness, reinforcement learning for variable stiffness and damping control. And everybody, many other people in the lab has contributed to this work. I also would like to thank the generous support of our sponsors. And thanks for listening, and I hope we get to talk in real life and not just me talking to my screen. So feel free to send me an email if you have any questions or to contact me in any way. My email, I realize you write it, is my first name, my last name. Thank you very much for listening to my talk.